Today we're going to talk about moisture. Uh, Water vapor or water is the only element that changes state in the atmosphere. In other words, it goes from a gas to a liquid to a solid. Uh, we see that in the sense that sometimes we know the air really is moist, feels really humid outside, but we don't see a cloud in the sky. That's because we have a big amount of water vapor in the air. Then other times you see a cloud up there, and that's when it's become liquid. And, in the wintertime it snows. And up in the clouds there's snow, many times even in the summertime. So all of these are the different ways that moisture transforms in the atmosphere. And we are all interested, is it going to precip? Or how much rain are we going to get? How much snow are we going to get? Is it going to be a pretty day? We're not going to have any clouds today. I want to go out and get a suntan or whatever. We're all interested in that. So, in order to forecast it, we need to know what's going on. So, I started right out by showing a satellite picture. It turns out that water vapor at different levels in the atmosphere emits infrared radiation at a different wavelength. So, we picked one here that's generally between 12 and 15,000 feet up, around 700 millibars, which is, a little on the lower side. It's not mid-level in the atmosphere, but it's kind of the mid-level as far as where the most moisture concerned. So if I was wanted to know if moisture was moving into my area, this would be the one satellite image if I just had one to choose from that I would want to see. So yellow is very dry air in this level. Green is very wet, probably where there's thunderstorms or rain occurring. So what are we looking at here? Well, let's go down here. We have a plume of moisture that's coming up in this area here. And you can see all the showers and thunderstorms in South Texas and all down here into Mexico. That is one area of precipitation. Its moisture literally is coming all the way off from down in the Pacific. We have other moisture down along the Gulf. Look at it coming up into Louisiana here, across Florida. Look at all the thunderstorms. All these dark green are thunderstorms here. And we have a cold front that's been working its way south across Virginia and down into Kentucky, Tennessee area. And there's some moisture down south of it in Kentucky and Tennessee and all. There's not a lot in Virginia. Matter of fact, I just have a few little clouds out popping along, but they're right along the leading edge of this boundary. And up here, stronger cold front, more moisture, and we actually have severe weather going on up there. So, great tool for learning where moisture is at and where it's moving. So, let's look a little bit now, switch gears. I want to know how much moisture is in the atmosphere. Particularly, we'll start with the lowest level, the surface. There's a parameter called dew point. You've all been looking at it when I've had you doing your different labs. We've discussed dew point. Dew point is taking the air in an area, cooling it to where dew forms literally on the ground. That's all it is. So the higher that number is, the more moisture is in the atmosphere. The lower that number is, the less moisture. In other words, in the wintertime, that number can go down below 0 Fahrenheit. So, yes, it can get pretty doggone low and pretty dry. In the summertime, notice here in Ohio, 75-degree dew point down here, 72 in Indiana. Fairly moist. However, if I go north of this cold front up here, 54-degree dew point, 48, 46, fairly dry. Another aspect of the dew point, I said that in order to get the moisture to condense, they have to cool to that temperature. So the further apart the temperature is from the dew point, the lower the relative humidity. Relative humidity is just a measure of how much moisture is in the air compared to saturation. Air is saturated when fog forms or cloud forms. So in this case, the further apart these numbers are, the drier the air, the lower the relative humidity. And we like cool, dry air sometimes. It feels good. Even warm, dry air feels nicer than warm, humid air. So you can look around and see up in here when you're just north of Wisconsin, Michigan. However, down here south of the front, well, 78 degrees here at Elizabeth City and 88 up here. It's a 10-degree spread, but that is a really high dew point. If there was precip, you might even see these being really close together. When it's raining outside, they may be only 1 or 2 degrees difference or even the same. If you have fog out there, probably the same temperature. So this is just another way of looking at moisture. And I would be very interested if I'm trying to follow these things, which direction is the wind blowing? Because that's taking the moisture. We talked about advection for temperatures. Well, we can advect moisture as well. So I am trying to, if I wanted to bring in very low dew point air somewhere, I'd be wanting the north wind up here, pushing this cold front south of me, and I would be advecting in drier surface air. Finally, there's one last topic we're going to discuss. I'm going to go into more detail. We're going to talk about stability. All right. Stability is, think about a hot air balloon. You see it rising up in the atmosphere. Why is it rising? Because it's lighter than the surrounding air. How is it lighter? Well, we know that heated air expands, so it pushes the molecules further apart. There's less molecules in one area compared to around it, where there are more molecules. So if you know the temperature of the air in a certain area, and I'm going to talk about parcels. Say an air parcel, if you looked outside and a cumulus cloud developing, that could be considered an air parcel. Uh, that might be what? A quarter mile across, maybe? Sometimes bigger. But that's just an example of an air parcel. And if that air parcel starts at the ground with one temperature and say around it, the general atmosphere around it is slightly cooler, that air parcel is going to rise. In other words, you found a hot spot. Some place got heated a little bit more than the surrounding area, so the air is going to rise up. As it's rising, it's staying, it's cooling dry adiabatically, probably just like the surrounding air, maybe. At some point, maybe it would even reach the same temperature as the surrounding air and stop rising. But up until then, it was unstable. Now, let's introduce moisture into this. That air parcel also has a little more moisture than the surrounding air. So what happens is it starts to condense. It reaches saturation. What happens when an air parcel reaches saturation? What does latent heat cause to happen? It causes to be latent heat goes out. It's released when we have condensation. So we know that moist adiabats, in other words, the temperature that now saturated air parcel is going to not cool as fast as the air near it, which is dry. So what happens is that air parcel gets more and more warmer, less dense. It's going to start accelerating upward, just like a hot air balloon would accelerate upward. Eventually, yes, it's going to reach a point where the temperature it has becomes the same as the temperature of the surrounding air. But on those days where it can really take off, and I have it sounding here for Lake Charles, Louisiana. Temperature is right here in red. Dew point is over here, a little bit further. What we have here is if I lifted an air parcel from this point, 850 millibars, and maybe a little bit of heating from the ground got going, maybe there was a warm sea breeze come in, push the air up. Something caused the air to rise to that point, and it became saturated right there, the bottom of a cloud. What happens? Well, if you follow it, it's going to always have the temperature of a moist adiabat, which would be right here. Notice how much warmer it is than the surrounding air. That's significant. That is very unstable air. So what is it doing? It's going to want to rise up all the way up to here. So that is a lot of rising air, probably up to about 40,000 feet or so. So you're going to develop a thunderstorm if you have enough that kind of thing going on. So this is very unstable air rising quickly, giving you thunderstorms. Sometimes it doesn't rise as fast. Maybe it will only just be right here, a little bit over. And maybe you're not going to get that today. Maybe there'll be all of a sudden a push of very dry air in there or something that mixes it out. But again, this is all we're talking about with stability. If the air parcel we're dealing with is warmer than the surrounding air, it's unstable. If it's colder, it's stable. That's all you need to know. You need to know how to calculate that in terms of whether it's actually happening or not. But, so let's take a look at this week's PowerPoint. All right. We'll do a quick slideshow here from the beginning of this. So we're going to talk about humidity. There are atmospheric rivers. I showed you one actually in the southwestern United States, uh, pulling up moisture from the Pacific into that area. These are just areas pulling in moisture over large areas. So almost all of the moisture is confined to the troposphere, and much of it is confined to the very lowest parts of the troposphere. So, with that being said, if you were to dump all the moisture out everywhere in the globe, every piece of moisture in the atmosphere out, you get a depth of about 1 inch. Doesn't work like that because it's different amounts of moisture, different places. So, how does this water cycle work? And we talked about it. You're going to talk about it in your discussion this week. Interestingly, in the Bible, it talked about this, and think about it. I am sure that they were an agricultural society beginning back then. They understood they needed precipitation. They may not have understood all the details, but God helped them to see that, okay, moisture evaporates, maybe over the Mediterranean, lifts up into the clouds, precipitation occurs. Oh, some of it fell back into the ocean. No problem. Maybe some of it fell on the eastern slopes or western slopes of these mountains. Ah, we got moisture here. It's going to run down the mountain slope. Maybe there was some more snow at the top of the mountains of ice. Oh, yeah, maybe that ice begins to melt, or maybe it becomes sublimates and puts more moisture back into the atmosphere. More clouds form. They rain on the fields, maybe. And if you look at it, when there's a lot of dry ground, there's really a lot of runoff, sometimes in the sand or whatever. If you go out to Arizona, there are areas that are very dry. And when they get heavy rain, all the water just kind of runs away from the sand. Yes, sand does suck up water with time, but initially the water just runs into these areas and really creates a new stream every time. They're just low spots. And if you're out there, there's big signs telling you when you're hiking, be careful when you're walking across some of these areas because they could flood very, very quickly. And I've been in some areas in Tucson where one day we had a thunderstorm, and that is a rare event, but it was a meteorological convention. We had a lot of rain, about a half inch, but the whole city had water all around. These little areas filled up with water very quickly because a half inch is tremendous amount of rain out there. Yes, it ran off with time into the bigger rivers or whatever. And some of this water actually goes down into the ground. There are massive amounts of water underground in the central United States, for example. So, as we talk about water, we talk about evaporation. condensation or transpiration. Oh yeah, the roots, plants release water. Sublimation, precipitation of all kinds. Humidity, I talked about it. All it is how close the air is to saturation. So, and we know that water vapor is a vapor, so it has pressure. And we've learned from Dalton's law that the pressure in the air is based on each one of the gas's pressure. So when water vapor is in there, it contributes to Dalton's law. All right. Some ways we measure moisture. Mixing ratio. I have a parcel of air. I have a mass of water vapor in that. And the remaining air is all dry. We'll take that little bit of water vapor and the rest of the air is dry. That is how you calculate as grams of water vapor per dry air. The remaining air that's dry, you measure water vapor over it compared to the dry air. Specific humidity, just add the moisture back in. All that mass is there. Absolute humidity is just, they're usually equivalent, like he says here. And saturated air. I want to know when the air is going to be saturated or if it is very close to saturation. And every one of these terms, mixing ratio, vapor pressure, all of that, we just put the term saturation in front of it. And that is the value that the air can hold before it becomes saturated. So heating air increases kinetic energy. So they more readily escape into water vapor. So in other words, the hotter the air is, the more water vapor the air can hold. That's all that's saying. So if it's really hot, I can hold a lot more moisture than if it's really, really cold. That is why you'll notice in the wintertime dew points are in the teens, maybe, or down in the single digits. In the summer, you just saw them in the 70s, almost 80. The air is hotter, it can hold more moisture, and it does typically. And then here is the chart showing that. Notice how it goes up pretty quickly, actually, once it gets warmer. Here's, 50 degrees, it's 12. Saturation vapor pressure now, then moving up steadily. Well, now I'm going to go to 23 at 68, and 77 is 31. That is a tremendous amount of water vapor compared to, in the wintertime, 6. Now it's 5 times as much. That's why when you walk outside in the summertime and it feels so humid and oppressive, there is that much more moisture in the air, making it feel that way to you. Now, remember, water vapor is lighter than regular air. So even though it feels like it, it's actually lighter. It's causing the air to become lower pressure. So relative humidity is just vapor pressure divided by saturation. It's percentage. When I tell you the relative humidity is 100%, they're the same, exactly the same number. So we know temperatures rise during the day. So in the morning, the relative humidity is going to be the highest, close to 100%, maybe even 100% if it's foggy. In the afternoon, temperature is going to be rising. It's going to hold more moisture. The relative humidity is going to drop off, even if the amount of moisture in the air has not changed. The relative humidity will drop. So that is why the lowest relative humidity typically occurs in the afternoon, unless maybe you're advecting moisture in or something. That kind of thing could change it. But other than that, you're always going to have the lowest relative humidity in the afternoon. Then the relative humidity is going to increase at night. Dew point, I've talked about it. Look at the difference in the wintertime for the summertime for dew points. In the wintertime, northern areas average 20 degrees or less dew point. In the summertime, notice much much more moisture in the eastern half, east of the Rockies. The Rockies are relatively low. So air becomes saturated because the air cools, the amount of moisture remains the same. It eventually reaches a point where it can't cool, can't get any more without being saturated. So you begin to get clouds. Here's the stability part again. Notice here, if the air parcel is warmer than the surrounding is rising, if the air parcel is cooler, and one of the things I want you to know is the air temperature dropping. It doesn't go at 9.8 degrees Celsius per 1,000 meters. More normal is about 7 to 7.5 degrees Celsius per 1,000 meters. So if I am pushing up an air parcel, it's very quickly going to cool if it's dry, faster than the outside environment. So it's probably going to get very stable very quickly and drop back down. Now, if I begin to heat that air parcel with condensation, now it's only cooling about 6 degrees for 1,000 meters. And if surrounding air might be cooling 7 or 8, the air parcel is becoming more and more unstable and rising. That is why condensation plays a big role in how much instability there is. If you actually have an air parcel that is conditionally unstable with a dry adiabatic lapse rate, which can happen near the surface of the earth, right by it, like within 5 feet of it, but that's about all. So what causes there to rise? Sun heating it, fronts, mountain ranges, any of them could push it up. Once it gets pushed up, it may form into a cumulus cloud like it shows here. And mountains, if you hit mountains, if the wind blows into them, they'll lift the air up, cause more rain on the side the air is blowing into than on the other side where the precipitation has kind of got sucked out of it. Happens in the Appalachians as well, believe it or not. When I worked in West Virginia, you could see east winds coming in off the Atlantic Ocean and dumping rain like crazy over in Roanoke, Lewisburg. You get over to Beckley or over to Charleston, West Virginia, or over to Huntington, the amount of rainfall drops significantly. Why? Because all the rain was coming on the east side of the mountains. So hope you got, we just talked about moisture. So I hope you got a little bit out of that. And please let me know if you have any questions.